So I would like to teach you this again. See, what is actually the observation made by classical mechanics people and the quantum mechanics people regarding the black body radiation. First of all, you should understand what is a black body. A black body is a device which can absorb and emit radiation of all possible wavelengths. So there is no ideal black body in the universe. But the most perfect black body was constructed by a scientist called Ferri, and it is called Ferri's black body. Look here, this is the construction of the Ferri's black body. And actually, the small opening here will act as the black body, which can absorb radiation of all possible wavelengths and which can emit radiation of all possible wavelengths when heated. It is a double walled system, and in between these two walls, it is evacuated. And the inner part of the Ferri's black body is coated with the lamp black material. And a small conical projection is made here to avoid the loss of radiation by direct reflection. Suppose a radiation comes inside and falls here, there is a possibility for it to get reflected and over there. So small conical projection is made so that the radiation which falls in will experience multiple reflection on the walls of the inner portion of the Ferri's black body, and the lamp black material which is coated here will store the radiation in the form of vibration of the carbon particles. Actually, the classical mechanics of people assumed that the energy which is stored in the carbon particles by vibration is stored according to equipartition principle, two modes of vibration, kT, so half kT into 2 to kT, and also they assumed that all the vibrators are vibrating with equal frequency. So if you come to know the total number of vibrators and the frequency of vibration, you can find out the energy of their vibration, because they assumed that all the carbon particles are vibrating with equal energy, and also it is according to the equipartition principle. But what this classical mechanics could not explain is this. Actually, the black body is emitting radiation of all wavelengths. See, from lower wavelength to higher wavelength, all wavelengths are coming out, no doubt about it. But when you plot the intensity and the wavelength, say suppose I'm taking a small wavelength here and I want to measure what is the intensity of that particular radiation. This is the actual intensity. When I go on measuring the intensity for different wavelengths, I am getting a particular wavelength which is coming out with the maximum intensity. There is a maximum intensity here. And also, when I rise the temperature, look here, at 800 Kelvin, the maximum intensity wavelength is this. When I increase the temperature to 1000 Kelvin, the maximum intensity is here. So when you measure this window, I don't know why it comes here. Just a minute. So when you raise the temperature to 1200 Kelvin, now That wavelength coming with the maximum intensity is here. When you further increase the temperature, the maximum intensity here. So the peak is slowly shifted towards the lower wavelength region. Initially, it was a higher wavelength that comes with maximum intensity, then a little bit lower wavelength coming with the maximum intensity, then still lower, then lower. Therefore, the peak is shifted towards the lower wavelength region. This is what is actually stated in the Wein's displacement law. So the Wein's displacement law states that the black body radiation curve for different temperatures will peak at different wavelengths that are inversely proportional to the temperature. So wavelength goes less and less and less when you raise the temperature. So look here, this can be very easily observed. Suppose if you take a filament bulb, the normal filament bulb, if you go on increasing the temperature of the filament by increasing the electric power, you can see that initially the bulb glows with a red color filament. So the filament will appear red because of the low temperature, because red has higher wavelength. When you further increase, it will become yellow. Yellow has lower wavelength. If you further increase, that will become white. And finally, it will blue and then it will blow off. Even when you heat a substance, suppose you are taking an iron rod and heating, first it will appear red, then yellow, and finally white. So the radiation that is coming out, its wavelength and intensity, when they are plotted together, when you raise the temperature, the wavelength that corresponds to maximum intensity is shifted towards lower wavelength region. Now, they wanted to arrive at a theoretical equation, an equation which will satisfactorily explain the curve which is experimentally found out. See, this is the experimental curve. When you plot rho lambda versus lambda max, versus lambda, you are getting a curve like this. Now, I want to mathematically derive an equation. I want to have a mathematical expression. When you draw a curve according to the mathematical equation, you should get the same curve what you get practically. Then, when the graphs drawn experimentally and theoretically are similar or appearing the same, then your explanation is the correct explanation. So people tried to find out a satisfactory explanation, but any explanation which is given for an experimental observation will be based upon some fundamental assumptions. So I've already told you what are all the fundamental assumptions of the classical mechanics. What are the fundamental assumptions? You can see the fundamental assumptions of classical mechanics here. There is no limit on the number of dynamical variables that can be determined accurately and simultaneously. And there is no limit to the values that a dynamical variable can assume. And there is no limit to the accuracy with which a dynamical variable can be determined accurately. And also energy changes take place in a continuous fashion. So with these assumptions, people started working. Because normally when we have a fundamental assumption, then we all our working and improvements and our construction of equations and our theories and our explanations, everything will be based upon that assumption. But there are possibilities that even our assumptions will be wrong. That is what has happened in this case. That's what has happened in this case. According to the basic assumptions of classical mechanics, the Rayleigh jeans and Wayne worked altogether. So they took the assumptions of a classical mechanics and the equipartition principle, and I have already told you what is an equipartition principle. Each mode of motion of a particle will contribute an amount of half kT to the total energy of the system. This is equipartition principle. So they have taken the assumptions of a classical mechanics and the equipartition principle, and they have formulated an equation which is called the Rayleigh-Jeans equation. According to that equation, dn, that is the fraction of number of vibrators into rho lambda, the peak, the intensity is equal to 8 pi by lambda power 4 d lambda. D lambda means it is the lambda gap. I am taking a particular lambda gap. In that lambda gap, what is the number gap of the vibrators vibrating? So when you the number, say for example, let me say the d lambda be some 1000 meter to 1100 meter. In that gap, what is the dn? The number of vibrators. And the remaining, it is the intensity, it is the lambda power 4. So rho lambda is equal to 8 pi by lambda power 4 into kT. I'm getting this kT from the equipartition principle. So each vibrator makes a contribution of a kT to the total energy of the system, where 8 pi by lambda power 4 is the total, let me say it is the number of vibrators. So the rho lambda will be this. So if you draw a graph according to this equation, lambda is here, 8 is a number, pi is a constant, k is again a constant, T is temperature at a particular temperature. So rho lambda and the lambda are inversely related. When lambda increases, rho lambda decreases. So you will be getting a curve like this. So what happens? Actually, original curve is like this, but the curve obtained from Rayleigh-Jeans equation is like this, which means that this particular equation holds good in the long wavelength region, because the curve, it increases initially like this and then comes down like this. So in the long wavelength region, this equation holds good. But this equation is a total failure in the lower wavelength region. So the Rayleigh-Jeans equation is successful in the longer wavelength region. So another scientist worked on the same problem with the same assumption. They did not change in their assumption. The Rayleigh-Jeans equation is finding its application in the ultraviolet catastrophe. So now we go to the Wein's equation. According to Wein's equation, rho lambda is equal to a constant C1 e power minus C2 by lambda t divided by lambda power 5. So rho lambda is equal to C1 by lambda power 5. See, just I have taken the lambda power 5 over here. And it is e power minus C2 by lambda t. So I'm taking this as 1 by e power C2 by lambda t. I'm just taking off the minus and I'm bringing this to the denominator. So according to this equation, when lambda value is very less, what will happen? C by lambda power 5 will increase and 1 by e power C2 by lambda t will decrease. So this particular factor increases, this particular factor decreases. For high values of lambda, this factor decreases, this factor increases. So when the lambda is low, this factor increases, this factor decreases, therefore it is going up. When lambda is high, this factor decreases and this factor increases. Therefore, what will happen? But the decrease is much faster than the increase. So what happens? The graph increases like this and then decreases like this. So I can say the Wein's equation holds good in the lower wavelength region, but it is a failure in the higher wavelength region. Whereas Rayleigh-Jeans equation was successful in the higher wavelength region, but it is a failure in the lower wavelength region. But Wein's equation is successful in the lower wavelength region, but it is a failure in the higher wavelength region. So what happens? I have to find out one single equation which will function as a Rayleigh-Jeans equation in the lower wavelength region and a Wein's equation in the higher wavelength region. I have to find out what is that particular equation. So in the year 1900, Max Planck came out with an assumption. See, that man simply changed even the fundamental assumptions of the classical mechanics. And he came out with a new idea called quantization principle. He said that the vibrators of different numbers are vibrating with different energies according to the quantization principle. And he also said the energy distribution is not continuous. There are discrete energy levels in which various numbers of vibrators are existing and they are vibrating with the different energies. And this distribution of energies with quantized energy states is called the quantization principle. So N0 number of vibrators are vibrating with E0 energy, N1 with energy h nu, N2 with energy 2h nu, N3 with energy 3h nu, and N4 with 4h nu, and so on. So where N1, N2, N3, N4 are a number of the particles, h nu, 2h nu, 3h nu, 4h nu are the energies, and these many numbers are vibrating with this energy, and these many numbers are vibrating with this energy, and these many numbers are vibrating with this energy, and this is the quantization principle. But according to the fundamental assumptions of classical mechanics, all vibrators are vibrating with one particular energy. So that is the difference between the assumptions made by the classical mechanics and quantum mechanics. So here it is quantized. The very word quantization, discrete fashion. The energy levels are not continuous. Energy levels are totally discrete and they are quantized. And in each quantum level, this is called a quantum level, a particular number of vibrators are existing. So I can say this a total number of vibrators, N is equal to N0 plus N1 plus N2 plus N3 plus and so on. Look here. So I can calculate the total energy where E is equal to N0 into 0 because it is assumed that the energy of the zeroth energy state is 0. N1, E1, N2, E2, N3, E3, and so on. According to statistical procedures, this is where the statistical mechanics is coming into picture. Statistical mechanics is the link between the classical mechanics and the quantum mechanics. According to classical equation, suppose if you want to find out the number of vibrators in the first energy state, you can equate the number in the first energy state with the first energy level. If E1 is the energy of the first energy level, then the number of vibrators in the first energy state N1 is equal to N0 e to the power minus E1 by kT. This is according to statistical mechanics. So similarly for N2, it is N0 e to the power minus E2 by kT. So N3 is equal to N0 e to the power minus E3 by kT. So from the equation 1, you can say the total number N is equal to N0 plus N0 e to the power minus E1 by kT plus N0 e to the power minus E2 by kT plus N0 e to the power minus E3 by kT plus and so on. So in order to simplify the equation, I am putting e power minus E1 by kT as x. So what will happen? This minus E2 is nothing but minus 2E1, because in the previous case we have said that this is H nu, this is 2H nu, this is 3H nu, this is 4H nu. Therefore, how this equation will become? Here it is minus H nu, minus 2H nu, minus 3H nu, and so on. So what I am going to do? So x is equal to e power minus H nu by kT means the equation will become n0 plus as n0x plus n0x square, because this becomes a 2e1, n0x cube because 3e1, and so on. So when I take this n0 out, I'm getting 1 plus n x plus x square plus x cube plus and so on. So this entire series can be written as 1 minus x whole power minus 1. So this thing you might have studied in the allied mathematics. You can expand 1 minus x whole power minus 1 as 1 plus x square plus x cube and so on. So what happens? This can be rewritten as n is equal to n0 by 1 minus x. Similarly, I want to find out the total energy. What is this total energy? First energy is 0. Then second energy is E1 into the number, that is N1, E2 into N2, E3 into N3, and so on. Similarly, I can put this particular factor as x. So what will happen? E1, N0, x. Then E2, N0, x square. What is E2? E2 is nothing but 2E1. E3 is 3E1, so on, so on. So when you take this E1 also out with x and N0, you are getting 1 plus 2x plus 3x square plus 4x cube and so on. So the equation, actually this series can be condensed to 1 minus x whole power minus 2. Or when you expand 1 minus x whole power minus 2, you are getting 1 plus 2x plus 3x square plus 4x cube and so on. So this equation can be simplified as n0 e1 x divided by 1 minus x whole square. So when you compare the equation 3 and 4, you can calculate the average energy. What is this average energy? Average energy is E by N. What is E? E is N0 E1 x divided by 1 minus x square. N is equal to, N is in the denominator. So I have taken the inverse. N0 divided by 1 minus x was original. I have taken the inverse 1 minus x by N0. So finally what I am getting? This square and this can be cancelled. It is E, this N0 and this N0 can be cancelled. What I am getting is E1x by 1 minus x. So when you substitute the x, E1, e power minus E1 by kt, 1 minus e power minus E1 by kt. So in order to simplify, I am multiplying the denominator and the numerator by e power E1 by kt, because I want to cancel out this minus. So what I'm getting is, so e power minus E1 by kt into e power plus E1 by kt will become e power 0. So it is e power 0 is 1. So in the denominator, I'm getting e power E1 by kt minus 1. So now I am substituting the value for E. E is H nu. So when you substitute H nu, it is H nu, that is in the place of E, H nu divided by e power H nu by kt minus 1. Right? So this is the average energy. This average energy, I am substituting in the place of the energy substituted on the basis of equipartition principle. You go back to the Rayleigh agency law. What is here? Rho lambda is equal to 8 pi by lambda power 4 kt. Kt is the energy obtained by equipartition principle. In the place of kt, I am substituting this average energy. So I am getting 8 pi by lambda power 4 h nu divided by h nu by kt minus 1. What is nu? nu is C by lambda. So h nu becomes hc by lambda. Here also hc by lambda kt minus 1. This equation is called the Planck's radiation law. So this Planck's radiation law, what happens? When the lambda is very large, when lambda is very large, this e power hc by lambda kt is much smaller than 1. So what I can do? E power x can be approximated to 1 plus x. So what happens? The equation becomes 1 plus, that is e power hc by lambda kt becomes 1 plus hc by lambda kt. So I'm substituting that 8 pi by lambda power 4. There is one hc by lambda and it is divided by hc by lambda kt minus 1. So this 1 plus and 1 minus get cancelled. What I'm getting is 8 pi by lambda power 5 hc by lambda kt. So what will happen? This hc will get cancelled. This lambda kt will go to the numerator. So what happens? It becomes, it is 8 pi by lambda power 4. It is, this actually this lambda has become here, lambda power 5. So 8 pi by lambda power 4 kt. What is this? Rayleigh-Jeans equation. When the equation became Rayleigh-Jeans equation at the higher wavelength region, where the Rayleigh-Jeans equation was successful in the higher wavelength region. Therefore, when the wavelength is higher, the equation becomes Rayleigh-Jeans equation. When the lambda is very small, then hc by lambda kt e power becomes much greater than 1. Therefore, 1 can be neglected. So when 1 is neglected, you are getting 8 pi by, actually hc by lambda, that lambda has come here, lambda power 5 divided by e power hc lambda kt. Now, put hc as, because h is constant, c is constant, c1. Here hc by k, all these things are c2. So when you substitute c1 and c2, you are getting lambda, rho lambda is equal to 8 pi by lambda power 5 c1 e power minus c2 by lambda t. This is Wein's equation. So one single equation is becoming Rayleigh-Jeans equation in the higher wavelength region and Wein's equation in the lower wavelength region. So Planck's equation is an interpolation of Wein's and the Rayleigh-Jeans equation. So the Planck's equation was successful in both higher and lower wavelength regions. So this is the wonder of a Planck's radiation law. What is the fundamental difference that Planck has made? He said that energy changes take place in a discrete fashion. Are you able to understand?